Hey everybody, it's Mr. Canfield. Today we are looking at the fundamental theorem of calculus. So this is going to be a fairly abbreviated version compared to what our book does, because unfortunately I've taken all of the fun out of the fundamental theorem of calculus by kind of spoiling it already. So today we're gonna talk about it and do a couple problems with it, but the big deal is that the fundamental theorem of calculus is the thing that links a derivative and an integral together. So there are some great notes here, but the main idea for us to get is that if we have some function called f of x, well then if we were to say, hey, f of x, let's say the derivative of that, we can call its derivative little f of x. The fundamental theorem of calculus links the derivative to the integral, and I've always kind of taken that for granted, and I shouldn't, because it's not just apparent. And if you're like, well, yeah, it is, it's because I told you about it. It's because that's what I taught you. So, or it's what your teacher taught you. Oh, the derivative and the integral, they're like opposites of each other, or they're inverse operations. Well, why? I'm not going to prove that for you today, but it's something that we get proven through math. So, but anyway, you can say the antiderivative, or the integral of f of x dx is equal to the original function plus c. Or we could do instead of doing an indefinite integral, we could say the definite integral from a to b of f of x dx, little f of x, is equal to its integral, or its antiderivative, plug in b minus its antiderivative, plug in a. So, yep. The fact that the integral and the derivative are linked is cool and really, really fundamental to calculus, which is why it's called the fundamental theorem of calculus. All right. Really going to get my mileage out of that note card that I made. Not note card, sticky note. That's what it is. Okay. So, the fundamental theorem of calculus lets us perform definite integrals with ease. So, this number 1 here, it says, hey, take the integral from 1 to 2 of x squared dx. And so all you have to do is take the antiderivative, which is, well, it's x squared, so it'd be x cubed over 3. And we're going to evaluate that from 1 to 2. So let me just double check Stu's notes. When I learned how to do this, we just drew like a bar like this. So I've seen this notation. This is like the notation that he uses, so I should try to use this notation. But we're just saying, hey, we're going to evaluate it from 1 to 2. And so all we do is we plug in the 2. So we get 2 cubed over 3 minus 1 cubed over 3. And so I get, 2 cubed over 3 is 8, so I get 8 thirds minus 1 cubed is 1, so minus 1 third. I get 7 thirds. And I want to make sure that I draw all the links and everything. And before I do that, though, I should go back, and I did not discuss in this video, I didn't discuss that I should have had a plus c here, or you might think that we should have a plus c. So let's talk about why I left out plus c. So plus c, some arbitrary constant. So what if we had kept it in? Well, then in this situation, instead of having 2 thirds over 3 minus 1 thirds over 3, wow, 2 thirds. 2 to the 3 over 3 minus 1 to the 3 over 3. Oh, goodness. So what if we had said 2 to the 3rd over 3 plus c minus 1 to the 3 over 3 plus c? So if we look at this, we get 8 thirds plus c minus 1 thirds minus c. What happens to those c's? Bop, bop. Oh. But what if c was a different number? Well, then it's going to be plus, if it was 15, it'd be plus 15 and then minus 15. What if it was minus 10? Well, it'd be minus 10 and then plus 10. Like, regardless of what c is, since it's the same number both times, it always cancels out. And that's why I didn't include it there. So let's talk about what this 7 thirds actually means. just to, keep this in context. 7/3 literally means take the curve y equals x squared, and it says from 1 to 2, right? So here's 1, here's 2. Take the area underneath this curve from 1 to 2. It's 7/3. This is the fundamental theorem of calculus, is wrapping integral with derivatives and puts it all in a nice neat package. So let's look at example 2. Okay. Sorry, I was debating. I was like, do I really need to do this? Okay. So if we've got this, well, then we're going to take the antiderivative of this, which is just, 3x squared. We're going to add 1 to the exponent, divide by the 3. And so the 3's will cancel. And we'll get x cubed. Negative 2x, we're going to add 1 to the exponent. Well, it is 1, so it'll go up to 2. And then divide by the exponent. So it's going to be just minus x squared. And then minus 1. 1 turns into an x. And we'll evaluate that from negative 1 to 3. So this is where it's very, very important that we're careful in the way that we show our work. So I'm about to plug in 3 here. So I'm going to write 3 to the third minus 3 to the second minus 3. And then over here, when we plug in our negative 1s, negative 1 to the third minus negative 1 squared minus negative 1. Okay, so this in general is a really important step for us to show. I should have even put those in parentheses there, those 3's. It's very easy to make silly mistakes on these. So when I'm going in, 3 to the third is 27. 3 squared is 9 minus 3. Let's see, so 27 minus 9 is 18. Minus 3 more is 15. So here, negative 1 cubed is still negative 1. Then negative 1 squared is 1, but subtract that. And minus minus, it's a plus 1. So those cancel. This is minus negative 1, this is plus 1. I get 16. So the exact area from negative 1 to 3 underneath 3x squared minus 2x minus 1 is 16. And I want to look at this in my calculator. That's not dead. Oh, sweet. I was like, this calculator's probably out of batteries. And it wasn't. I don't know why I'm talking like this. All right. Wait. I'm feigning surprise right now. I was expecting this. I was like, oh, I bet this example goes under the y-axis. So let's see, we're going from negative 1 to 3. So if I look at this, so we should talk about what this number 16 actually means in context of this problem. There, perfectly to scale. Now, okay, so I know there's some problems with this, but so what winds up happening is we have this. There's 1, here's 2, here's 3. Anyway, so we're looking at, this is actually what it's looking at. So let's say here's 1, here's 2, here's 3. So it's like all this is what it actually is. And what happens is the way that integrals work is it actually looks at this as this is the accumulation of all this area. And so we talk about area above the x-axis as being positive and the area below as being negative. And so and I like to use that snowfall analogy. You know, here we're gaining snow, here snow's melting, and here we're gaining more snow. So because of that, yeah, we have this really positive piece here that we're tacking on, but we've lost a little bit in the middle. If we hadn't lost this little bit, this number would be even higher. So, yeah, that's what's going on with that picture. And we actually are able to do this in the calculator. which I'll show you. Just drop the calculator on the floor. All right, so here's my graph. Let me zoom out just a touch. So I want to get all these y values in there. Let's have the y go to like 50. Let's see if that's enough. That looks like it'll be enough. So so if we go in and we do second calc, we actually can go down here and calculate an integral via the graph. So the lower limit, we're going to go down and we're going to go to, I think I actually type it in, -1. Yeah, lower limit's -1. And I'm going to set the upper limit at 3. And it's showing us the shaded region here. And so, and it says that it's exactly 16. So that's pretty cool that we can do that. And if I had zoomed, more standardly, well, no, we wanted, let's say that we're going from -1 to 3, and let's set our lowest y value at like -2 and our max y value at like 20. Let's see if we can see it. Whoa, what did I do wrong? Oh. That was it. Okay. So now we can basically see our whole picture. And if I do the same thing again, where I go second trace and go all the way down to the integral, and say my lower limit, I'll type in -1. I'll say upper limit, I'll type in 3. And we can see that this whole region here, all that shaded region, adds up to 16. So it'll be like this positive, we lose some, and then we gain more. So that's that. Example number 3 takes the integral from 0 to 9 of the square root of x dx. And so remember, we're going to take the antiderivative of this. So we want to think about this as the antiderivative of x to the 1/2 dx. And so to take that antiderivative, we just add 1 to the exponent. So we get x to the 3/2, and then divide by 3/2, which is 2/3. Sorry, we'll just multiply by 2/3. And we'll go from 0 to 9. And just a heads up, this would not be a calculator question. They expect that we know how to do this. So I'm going to go through and do the math, the explanation of how all the pieces work, how everything happens. So we can leave the 2/3 out front of everything. And then it says x to the 3/2. So that's going to be 9 to the 3/2 minus 0 to the 3/2. So since they both have a 2/3, I'm just factoring it out, and I'll multiply that back in later. All right, 0 to the 3/2. Think with me now. It's going to, no, just kidding, it's 0. So, but 9 to the 3/2. What's really happening here is this is saying take 9 and cube it, and then take the square root of your answer. Now, you may be comfortable cubing 729, or square rooting 729. I'm not, because 9 cubed is 729. I'm pretty sure. Memory serves correctly, cool. Instead, what I'm going to do is I'm going to say, hey, I'm going to take the square root first and then cube it. So the square root of 9 is 3, and then 3 to the 3rd, well, 3 times 3 times 3 is 27. So this is 2/3 times 27, and so that's 2 times 27 divided by 3, or I can divide by 3 first, and this turns into 9. So 2 times 9 is 18. So from 0 to 9, I think this is the last one that I'll show. I think this is good enough. So if I say let's go from 0 to 9, and look at our graph, this is saying the total area under this curve from 0 to 9 is exactly 18. Oh, perfect. So I don't know if you can see on my calculator screen, it says 18.000045. This is called round-off error. We have things like this that happen all the time. It uses a very, very powerful, the calculator is using a very, very powerful, tedious technique to essentially do a Riemann sum. And that's what's going on here. It's just adding up a bunch of little areas and it's getting our answer. So that's why when it does that, there can be slight little differences because it gets basically close enough and it doesn't get accurate enough. Okay, number 4 says the integral from 5 to tan of 2 over 3x squared dx. All right. So on this one, I'm going to dress this up a whole bunch before I take the antiderivative. It's actually a very easy antiderivative. And I'm going to, kind of chunk this out into all the steps that it is. First thing I see is this is 2/3 times 1 over x squared. And then the next thing I'm going to do to this is pull the 2/3 out front. And I'm going to change 1 over x squared to x to the negative 2. Now we have a super easy antiderivative. I'll add the 1 to the exponent, get x to the negative 1, and then divide by my new exponent of negative 1. So then I've got 2/3 times the integral. And so I evaluated the integral from 5 to 10. I almost wrote plus c out of habit there. So I'll get my answer, and then I'll simply multiply by 2/3. So let's see. First I'm going to plug in 10, so that's negative 10 to the negative 1 minus. Now this is where, these parentheses can be really helpful. I wasn't about to use them. So we can say this is negative 5 to the negative 1. So that's actually going to turn into a plus. So to the negative first power means it gets flipped. So this is negative 1/10 plus 1/5. And then whatever we get there, we'll multiply by 2/3. So I need to get these to have the same denominator. So I can make them both 10s. So if I multiply this by 2 over 2 over 2, I'll get 2/10. So negative 1/10 plus 2/10 gives me 1/10. So I have 2 over 3 times 1 over 10. So I get 2 over 30 or 1 over 15. So how is that from 5 to 10, that only adds up to a 15th? Let's see what this looks like. I know I said that the last one was going to be the last one I did, but I'm really curious. So I'm going to go from 5 to 10. Hello? Where'd you go? Let's just zoom standard and see if we can see it. Oh. That's why it gets so close to the x-axis so fast that when we add up that, let's look at our y values here. What do we have? Let's see, 5, 6, 7, 8, 9, 10. Yeah, look at all those tiny y values. So I'd be thinking about adding those rectangles together. We're gonna get something really small, and we're not talking about rectangles here. We're talking about the exact area. So there we go. Let's see, 5. All right, 5. There are multiple ways for us to approach 5. I'm gonna do some advanced integration conversation on this one. So I'm gonna use my problem solving hat. So let's see, I'm gonna do this my way, and then I'm gonna say or this. So my gut reaction is I can do u substitution with this really easily. And say u is equal to 2x minus 1. So then du is going to be equal to 2 dx, divide both sides by 2. So I'm going to say 1/2 du is equal to dx, and then say that this is the integral from negative 1 to 1 of u squared with a 1/2 out front du. So I get u cubed over 3 with the 1/2, so u cubed over 6. And then I just got to drop the x stuff back in. So 2x minus 1 cubed over 6, evaluated from negative 1 to 1. Yeah, so that's the way that I thought about doing it. I was like, ooh, I can use u substitution. Let's try the other way. So the other way would be, oh, well, why don't we just say that, square it out and get 4x squared. Then we'll get minus 2x twice, so minus 4x plus 1. Why don't I just do this? So I get 4x cubed over 3 minus 4x squared over 2 plus x evaluated from negative 1 to 1. So for me, I wanted to do all that work instead of that work. Maybe I should have worked smarter and not harder. So anyway, when I plug in my values, I'll get 4 times 1 cubed over 3 minus 4 times 1 squared over 2 plus 1 minus, somebody did not include enough space here, minus 4 times negative 1 cubed over 3 minus, 4 over 2, I can just write that as 2. That's just a 2. Minus, 4 times negative 1 squared over 2 plus negative 1. All right. And so now if I'm careful, which I need to be with this, calculation is very, very easy to make mistakes on. So 4 times 1 cubed, well, it's 4 times 1, which is 4. So I get 4 over 3 minus 2 times 1, so just 2 plus 1. Let's see, now let's think about this. Let's just leave that minus there and just be careful. So this is negative 1 cubed is still negative, so it's going to be negative 4 over 3. This squares out to a positive 1, and that's just going to be minus 2. I did all that talking about that, and I didn't even do it there. Oh, silly me. And then that's still going to be minus 1. So now I'm going to have to distribute this negative. So I get, 4 thirds. Now I can do minus 2 plus 1 and write that as minus 1. And then say plus 4 thirds. This is going to be minus 3. So minus 3 is plus 3. So 4 thirds plus 4 thirds is 8 thirds. That's going to be plus 2. And then I can get this to be over 3 if I do times 3 times 3. Times 3 over 3. So it's 6, so I get 14 thirds, which would be what, 4 and 2 thirds, or so 4.6 repeating. So I do 2x minus 1 squared from negative 1 to 1. So then if I do second trace and go down to do the integral, do negative 1 to 1. Yep, 4 and 2 thirds. So, cool. Let's keep going. 6. I'm not going to do 6 in its entirety. I just want to talk about one thing with 6. No, do 6. Because if you don't want to see it, you can just skip it. So here's another one where we're going to have to dress up a whole lot before we actually take the antiderivative of it. So 1 to 8. First thing, this is x to the 1/3 on the bottom. And I can rewrite this as x over x to the 1/3 minus 2 over x to the 1/3 dx. Or, remember we subtract exponents. So 1 minus 1/3 is 2 thirds. So 1 to 8 of x to the 2/3 minus, and that's, since it's on the bottom, it's to the negative 1/3, you could say 2x to the 0 minus 1/3. So it's 2x to the negative 1/3. And now when we take the antiderivative of this, we get x to the, add 3 over 3, right? Because we're adding 1. X to the 5/3 times 3/5. And then this will be x to the 2/3 times 3 over 2, right? So 2x to the 2/3 times 3 over 2. I was going to cancel those, but I didn't want to, I was going to just not write them, but I didn't want to confuse anybody. So, and now we're going to evaluate that from 1 to 8. So, you know, I'm glad I'm doing this problem because it gives us another chance to talk about how fractional exponents actually work. So, okay, so let's see. Let me try plugging in the x's in a different color. So we're going to have 3 over 5 x to the 5/3 minus 3 x to the 2/3 minus 3 over 5 x to the 5/3 minus 3 x to the 2/3. Okay, and remember that we're plugging in 8 first. We plug in the upper bound first, then we'll plug in the lower bound second. Okay. So 8 to the 5/3. Remember, easiest way to do this is take the cube root. Take that bottom number as the root. Do that first. Cube root of 8 is 2. So cube root of 8 is 2. So then 2 to the 5th is 2 times 2 times 2 times 2 times 2 times 2, 2 times 2. I think I said it too many times. Whatever. 2 to the 5th is 32. This is 3 times 32 over 5. Ew. That's fine. And then here, we'll take the cube root first, and we get 2 times 2 is 4. This one, much easier. Take the cube root of 1, you get 1. Take it to the 5th power, you get 1. That's 1. So we get 3 over 5 minus 3. So I'll distribute my negative. I'll get minus 3/5 plus 3. This is minus 12. And then here, this is, well, that's going to be 96 over 5. All right, 96 over 5 minus 3, that's 93 over 5. Minus 12 plus 3 is minus 9. So I got to do times 5 over 5. So I get 45 over 5. So 93 minus 45 is going to be 48. So 48 over 5, final answer. All right. Let's see what's next. All right. Yeah, these last 3 are still good. So what can I say? These are great examples. So 7 goes from 0 to pi, 2 plus sine x dx. So pretty straightforward. We know the antiderivative of 2 is 2x, and the antiderivative of sine is whatever I took the derivative of to get sine. So I took the derivative of cosine to get sine. But wait, when I take the derivative of cosine, I get negative sine. So the derivative of negative cosine will get me sine. And we'll go from 0 to pi. So all we got to do is plug in pi first. So that's going to be 2 times pi minus cosine of pi minus 2 times 0 minus cosine of 0. And if we do that, then we'll get, well, 2 pi is 2 pi. Cosine of pi is negative 1. So negative 1 is plus 1 minus 0 plus, right, because that minus gets distributed, plus cosine of 0, which is just 1. So we get 2 pi plus 2. This is how you'd see your answer. You wouldn't get like 8.28 or whatever. Let's see, 8 goes from 0 to pi of a fois of 4x plus secant squared x dx. You might notice I don't write the parentheses. It's understood that there are parentheses in between those two, as long as the stuff is in between the integral symbol and the dx, at least as far as I get it. So this is another pretty straightforward integral. I'm just going to put the equals down here. So 4x is going to turn into 4x squared over 2. I'm going to write that as 2x squared plus, what did I take the derivative of to get secant squared? Well, it's just tangent. So tangent x, we'll evaluate from 0 to pi over 4. So pi over 4 is like the best tangent ever. So let's see, we'll have 2 times pi over 4 squared plus tangent of pi over 4 minus 2 times 0 squared plus tangent of 0. So I'll kind of walk you through, just to remind you how I calculate these. So, well, pi over 4 is we're going to have to square both of those and get pi squared over 16. And there's a 2 on top, so the 2 and the 16 can turn into a 1 over 8. Pi squared over 8. Don't care what number that is. Sure. Fine. What decimal is this approximately? Pi squared divided by 8. Oh, 1.23, whatever. Okay, so yeah, we get some number. Tangent of pi over 4, remember. So pi over 4, if you remember, is a 45-degree angle. So here's our angle. So if it's a 45, it's a 1 root 2. 45, 90. So then tangent is opposite over adjacent, or just 1 over 1. So plus 1. The other way we do tangent of pi over 4 is we use our unit circle. Go out to 45 degrees. Remember that that's root 2 over 2, root 2 over 2, and then do sine divided by cosine, which is y divided by x, which is 1. Then this one, tangent of 0. Excuse me. We'll just remember that, well, let's see, this first part's 0. Tangent is 0. That's going to be right here. What's our tangent? Well, it's 0, 1. Y was 1, x was 0. 1 divided by 0, 0. Oh, so it's just pi squared over 8 plus 1. There we go. All right, and number 9. All right, I don't want to show you how easy this is in the calculator, because first we need to talk about this. We have not talked about the antiderivative of absolute value, and in reality it's actually very messy. Well, actually, no. Let me say in reality I don't know the antiderivative of it. I know the derivative of it, and that's kind of messy. But anyway, the way we find this integral is really if we kind of think about what this shape looks like. So we know the absolute value looks like a V. Normally, the absolute value of x, wow, I wrote high instead of writing absolute value of x. There we go. So normally the absolute value of x is centered at the origin. And then finding, we could just find the area of those two triangles. We wouldn't even need anything fancy. So instead, let's find out when this hits the x-axis. So it normally hits here. When would this hit the x-axis? Well, 4 minus 2x, well, it's going to hit when x is 2, because that's when we get a 0 out. And then, so we know that from 0 to 5, 1, 2, 3, 4, 5. I'm not like playing a game right now. This is me actually doing the problem right now. So I know when I plug in 0, I get 4 minus 0, so I get 4. And because of how absolute values work, I know that these are going to be connected. And then I just have to find out what happens at 5. So if I plug in 5, that's 4 minus 10, which is negative 6. And then absolute value is positive 6. 1, 2, 3, 4, 5, 6. So then it's up here. Pretend it's a straight line. So now I've got a triangle here that's 4 and 2. Okay, so 4 and 2, that's going to be 1/2 times 2 times 4, which is just going to be 4. And then this one is 1/2 times, let's see, 1, 2, 3. Base was 3, and then height was 6. So 3 times 6 is 18. Half of that's 9. So 4 plus 9, I get 13. All right, this is where doing area is so much easier than actually going through and doing the real integral of this. And here's what I mean. The integral of this, if I was going to turn this into something that we can handle, we're going to say, oh, we'll go from 0 to 2, and we'll just do normal 4 minus 2x dx. Then we're going to add that to go from 2 to 5. And instead of doing 4 minus 2x, we're going to do the opposite. We're going to do negative 4 plus 2x dx. And that's how, and if you think about that, it's because these were negative values. We had to take the opposite of them to get them positive. And That's what's going on here. So now, instead of just taking this, breaking it up, and finding this area, finding the areas separately, we can do this. And I'll just show you real quick on the calculator. Just in case you didn't know, if you push the math button, go over to num, that very first option there is absolute value. Look at this. Look at absolute. Whoa, zoom back to standard. Okay. Look at my absolute value graph. Whoa, so cool. And then if I do second calc and I go down to do the integral, I can go from 0 to fiv, and boom, there we go. 12.909 repeating, or turns out it's 13. So cool. Additionally, you could do this. Let's see. We just crossed a half an hour. Let me show you one more thing that we can do. So you can find the integrals on this. You can also, instead of doing that, if you push math and go all the way down, we had the n derive we used for derivatives. We also have this one. And I'm going to call out some friends from, reminder, Canfield, never put things in the shadow zone. Okay. So, friends from high school, it says f and int. So I had a friend who always called this the f and integral. He didn't say the actual word, it says fn. And we thought that was hilarious. Inappropriate. So here I can literally say, let me go from 0 to 2 and type in my function, 4 minus 2x. And here we have to put dx, that's the variable we care about. And I can add that to, I could even see, I could push enter and see that my first triangle did in fact have an area of 4. And then I can go back and go all the way down to the f and integral, 2, 5, negative 4 plus 2x dx. And push graph. And we'll get 9. There we go. And if we'd wanted, we could have done them, in one line and added them together and gotten 13. So, multiple ways to do the same problem. I prefer using this to find integrals as opposed to using the graph, although the graph does look really cool. So, it's a matter of preference. Let's see. I think that covers everything. So, hope this was helpful, as always. Yeah. Talk to you next time. Bye.